I'm happy to introduce Rebecca Willett for this. I think it's the, let me see, it's the fourth or fifth installment or the fifth presentation in this mini tutorial session in SIAM conference on mathematics for data sciences. And Rebecca will be talking about learning to solve inverse problems in imaging. And yeah, sorry. She's a professor of statistics and computer science at the University of Chicago. And her research interests span over signal processing, machine learning, and I would say large-scale data science in general. With emphasis on the applied side, she's been working with imaging problems and also network models. Motivated, the latter motivated typically by wireless network services or social networks. She has a wide range of applications, actually quite a broad range, ranging from sciences to almost social sciences, almost I would say. And she's also been looking at mathematical foundations of signal processing and machine learning in this context, not only about solving real-world inverse problems. Rebecca received her PhD in 2005 from Rice University. And right afterwards, she was actually an assistant and then tenured associate professor at Duke, which lasted until 2013. From there on, she moved to University of Wisconsin-Madison, where she remained until 2018, again as an associate professor. And I believe from there on, she has been at the University of Chicago as a professor in statistics and computer science. She has been a recipient of numerous fellowships and scholarships. And among the awards that, to make this long list short, is worth mentioning will be the National Science Foundation Career Award that she got in 2007. And she was also awarded the Air Force Office for Scientific Research Young Investigator Program, that's a long title, in 2010. And I think, yeah, I think the floor is yours, Rebecca, so I will be muting myself. Just before I leave over the word to Rebecca fully, as we said, these sessions are recorded. So for everybody, for everyone, you can attend them. You can actually watch them later on. They are also live streamed on YouTube. And I'm posting the link to the YouTube channel where you can, I think there's a day or two delay before the presentation pops up on YouTube. And a practical matter, if you have a question, you raise your digital hand. You should be able to do that. The attendees are muted. The panelists are not. They can unmute themselves. But attendees are muted. You raise your digital hand, and if it's very urgent, you can write a message on the chat line directly to me or Carola. Say that you really want to ask the question, in which case we will unmute you at a suitable time, and you have the chance to ask your question. But preferably, we take the questions at the end. Having said that, I now leave the word over to Rebecca. Please, the floor is yours.
Great, thank you very much. Thank you for that very kind and flattering introduction, and thank you so much for inviting me to be a part of this series of tutorials. I'm sorry we can't all be together in person, but I've really been enjoying many of the talks, and I'm excited to be a part of this. Also, I am very happy to answer questions throughout as they arise, so please don't be shy. So what I'd like to talk to you today is about some methods for trying to solve inverse problems in imaging, where we use training data to improve the efficacy with which we can learn these solutions. So what I mean by this, our general setup is the following. We're going to assume that we observe corrupted, noisy images of the image of interest, beta. So beta is the image of interest, X is our observation, and X is a model of how the image has been corrupted, or a model of the imaging system used to collect our data. And then epsilon would be some noise. So our goal here is to recover beta from Y. And examples include many classical problems, including in painting, where we only observe a subset of the pixels of the image and we want to fill in the missing pixels, deblurring, super resolution, MRI reconstruction, radar, tomographic reconstruction, and many, many others. So this is an old problem that's been studied for decades. And of course, given the sort of linear system of equations perspective that I just presented, the first thing that many of us would think of would be just trying to use least squares. So we could examine this in the context of deblurring, where we see in the upper left here an image that is blurred. And if we just take that blurry image and try to compute the least square solution with full knowledge of the blur operator x, then we get an accurate reconstruction of the image. But if that blurred image is contaminated by even a very small amount of noise, like we see in the upper right, so visibly you don't see the noise at all, but even then, when we try to apply the least square solution, we can get something that's wildly different and corrupt. And the issue lies in the fact that for this deblurring problem, x transpose x here is going to have often eigenvalues that are very, very small. And so when we invert them, and then those get multiplied by the epsilon, that's a component of y, the noise epsilon gets amplified by the inverse of those small eigenvalues, and we just get these huge distortions. And so one approach to sidestep this is classical methods like Tikhonov regularization, or in the statistics community, it would be referred to as ridge regression, where instead of trying to minimize the square difference between our data and what we would imagine we would collect given a candidate image beta, we tack on a regularization term, something that says what kinds of structure in beta we'd like to promote or we think are more likely. And in this case, that regularization term corresponds to a tuning parameter lambda times the square of the sum of the squares of all the pixels in the image beta. And so this is going to prevent this terrible solution that we saw with least squares, because in this solution, many of the pixel values just have enormous magnitudes. And another way of looking at it is that we take all of those tiny eigenvalues and we add a little lambda to each one of them so that the overall system now is much better conditioned. And so if we apply this, then we get a reconstruction that is obviously much better and much more robust to noise, though admittedly pretty imperfect. So this notion of using regularization, of course, has been explored pretty exhaustively in the intervening time. So methods like total variation regularization, which look at first order pixel differences, wavelet sparsity regularization, or even methods based on subspaces or unions of subspaces or manifolds of patches within images, can all be thought of different ways of trying to take geometric models of images and use those to promote good solutions to inverse problems. So what I'd like to discuss today is another sort of perspective on these approaches, where we're going to consider the general framework of trying to find an estimate of our image beta by searching over all candidate images and finding the one which first is a good fit to our observed data, but also has a small value for some regularization function. And the question is, if we don't know ahead of time what a good regularization function is, but we have at our disposal a large collection of training images that all represent the kind of geometric or other kinds of properties of the images that we want to reconstruct, can we use that to learn a good regularization function and produce good estimates beta hat? So this is a question that a number of people have investigated over the last several years. There's many, many papers on it. At the bottom here, I'm citing a couple papers that are much more tutorial in nature, that give an overview of the different classes of different approaches and some of the trade-offs associated with them. And of course, the first one is by our host here, Ozam and Carla. And so what I'd like to do in that vein is, instead of going through a list of many, many different approaches, I'd like to describe some of the broad categories of approaches that people take to solving these inverse problems. In particular, the four categories that I'm going to describe today are model-agnostic, where we, for the most part, ignore precise knowledge of this forward model X; decoupled, where we somehow separate out the process of leveraging knowledge of the forward model X and where we learn from the training data; then unrolled optimization, and finally, a newer method that my student Davis Gilton and a postdoc Greg Angie and I developed together called Neumann networks. So let's start with this model-agnostic approach. And this is an approach that's been explored from a variety of different perspectives in a variety of contexts. And again, Ozam and Carla did a paper with a notable example of this a couple of years ago. But on a high level, we can think about this general framework as the following. We would take our raw data, Y, which in the context of super resolution would just be the low resolution image. And then from that, we produce some sort of coarse initial estimate. So in this case, for super resolution, we might do that by doing some sort of bicubic interpolation. In other cases, you might just try to do some sort of unregularized least squares. But in any case, you come up with some coarse initial estimate. And I write here X tilde inverse to indicate that somehow this coarse initial estimate might reflect some level of knowledge of what X is. Like in this case, it reflects the fact that we want to scale up the resolution. But it's by no means sort of a precise model of X that's been precisely inverted. So once we have this initial coarse estimate, then we try to produce a finer, higher quality reconstruction or estimate. And we, in fact, would train something like a neural network to learn a mapping from this initial coarse estimate to this high quality, high resolution estimate. And so from this perspective, I call this agnostic because it's not really using precise knowledge of the forward model X, except in this initial stage. And the role of the learning and the role of the training data is really to compensate for any deficiencies in this first initial reconstruction. Okay, so that's the first kind of class of methods. Arguably, it requires more training data than a method that would leverage more precise knowledge of X. Because the less knowledge of X that we utilize, the more we're forced to sort of learn during the learning process. Another way of thinking about that is, in this case, the worse this initial reconstruction is, then the more heavy lifting our neural network is going to have to do, and the more training data we're going to need in order to learn how to do that, to learn how to compensate for the errors in that initial estimate. Okay, so now we can return to methods that try to exploit more precise knowledge of the forward model X, and we're going to look at decoupled approaches. So what I mean by that is the following. In fact, I want to introduce this through the context of two different examples. The first one is called deep proximal gradient, and variants of this have been explored throughout the literature. So the way we're going to approach this is we're going to say, just imagine for the moment that we already know what regularization function R we're interested in. Then how would we solve this optimization problem? Well, what we might use would be a proximal gradient optimization algorithm, where we start with some initial estimate, say beta hat 1, and some step size eta. And then we would iterate. And in each iteration, we would essentially take two steps. In the first step, we would take our previous estimate, beta hat k, and we would update it by taking a step in the direction of the negative gradient of our data fit term. Second, we would take that the result of that, and we would regularize it. So we would nudge it towards something that has a lower value of this regularization parameter. And when I write this proximal operator or this nudging step like this, it might remind many of us of a denoising problem or of an inverse problem where the forward model is just the identity matrix. All we're trying to do is trying to find an image beta that is close to this zk and has a small value of this regularization parameter. And so we alternate between those two steps, this gradient descent step and this denoising step. And so from this perspective, we can then say, all right, well, if I don't know a regularizer beta, but I know that what I'm ultimately going to need to do reconstruction is to know how to use the regularizer to do denoising, then what I can do is I can just replace this whole denoising step with a learned neural network. Or in other words, I can train a neural network to essentially perform denoising. And once I've got a system that can do denoising, then I can plug it in to this proximal gradient algorithm for any new inverse problem X or forward model X that you might come up with. And that's why I call this decoupled, because I first take all of my training data and I learn a denoiser. And this denoiser is independent of whatever X is. And then once the training is done, I fix the neural network, I fix the weights, and then I plug it into this proximal gradient algorithm and use knowledge of my forward model. And so that I somehow am not using the forward model during the training process. Okay, so this is one example of a decoupled method. Here's another one that's received quite a bit of attention, where the idea is, imagine that all the images we care about lie on some low-dimensional submanifold. And we could imagine in this case then setting a regularizer to be 0 whenever the image is on the manifold that we care about and infinity otherwise. So if that's the case, then we might try to take that knowledge and use training data to learn something about this manifold and then use it within this framework. So specifically, we could use things like generators, things like generative adversarial networks, for instance, in order to represent the structure of that manifold. So a generative model, as I've sort of illustrated at the bottom of the slide here, would take an input, a lower dimensional input, say Z, feed it into this generative model, a generative neural network, and would output some image, in this case, a face. And so we can then think about the generative model, or all the different possible outputs of the generative model, as representing that manifold structure that we're interested in. And so if we have a good generator, we can write a regularizer as being either 0 for any image that's in the range of the generator and infinity otherwise. So now what we can do is we can take our training data and learn this generative model. Again, now we're going to stop all of our training. And once we have that learned generative model, we just plug it in to an inverse problem solver. So in particular, we would choose our estimate beta hat to be the beta in the range of the generator that best fits our data. So here's an example of this idea in action. I've got the original image beta, an observation with a bunch of missing pixels, and a reconstruction trained with 80,000 samples. And you can see it's doing a pretty decent job. But if I were to reduce the number of training samples down to, say, 2,000, this method completely breaks down. And I want to emphasize that this is not unique to the two approaches that I just described, but rather this is a general phenomenon that we see when we're working with these decoupled methods. And so the question is why? What's going on here and what's causing this extreme sensitivity to the number of training samples? Now, before I kind of go into answering that question, I just want to emphasize thinking about sensitivity to the number of training samples is relevant in a number of applications. So all you want to do is reconstruct images of cats, then there's arguably an infinite supply of training data, and this is not too problematic. But many applications, including things like medical imaging, getting large quantities of high quality training data is much more challenging. And so having methods work well with small numbers of training samples is very important. Okay, so let's just think about why some of these decoupled approaches might be ineffective or problematic. So the way we're thinking about generating these regularizers and using them, under the hood or implicitly, corresponds to trying to use our training data to learn some distribution over the space of images, some prior, if you will, P of beta. And once we know that prior, then we can use it combined with the data likelihood, say our squared error data fit term, in order to come up with an estimate that's a good fit to the data and conforms to our prior. But in the context of something like inpainting here, we can see that in this image, there are tons of pixels that are totally irrelevant to the inpainting problem. So if I want to fill in the details of her nose, that's totally independent of the color of the background. The fact that the background is blue doesn't tell me anything about the structure of her nose. And so if we take our training data and we force ourselves to try to learn the full distribution over all possible images, then we're really having to learn way more about the structure of images than we ultimately need to solve the inverse problem. And so what I would argue is that the more relevant quantity is not the full prior distribution, but rather the conditional distribution of, in this case, the conditional distribution of all the missing pixels given the observed pixels. Or in other words, we could think about this more specifically as the conditional distribution of x perp beta given x beta, where x perp beta would correspond to all of the directions that are orthogonal to the range of x. Okay, so there's a wealth of literature about conditional density estimation in statistics in particular that has illustrated that there are many cases where the conditional density can be lower dimensional or smoother than joint densities or full densities. And so as a result, if we think about how much data we need to learn a conditional density up to a target level of accuracy, it can be significantly lower than the amount of data that we need to learn the full density to the same level of accuracy. A slightly less hand-wavy explanation of why the conditional density is probably the right thing to target comes from the perspective of minimal mean squared error reconstruction. So let's think about rho as corresponding to some mapping from observations to an estimate beta. What we'd like to be able to do is to find the rho, the inverse problem solver, that's going to minimize our mean squared error, right? So anytime we come up with some strategy, it corresponds to some rho, and we want to find the optimal strategy, rho star. So what we can show is that this rho star has a very particular form that I've shown towards the bottom of the slide here, where rho star for a set of observations y corresponds to the pseudo-inverse of x times y, plus this x perp that we just talked about, transpose, times the conditional expectation of x perp beta given x pseudo-inverse times y. So when we look at this, we see there are basically two terms. The first term is something that's known, and we can just flat out calculate. And the second term is essentially what we don't know and we'll have to learn from data. And we see that the thing that we have to learn from data corresponds exactly to this notion of a conditional density that I just described on the previous slide. Okay, so all of this is to say that if we know x, then trying to estimate the conditional density directly can require far fewer samples than estimating the full density. And so whenever x is known, it really should be utilized in the learning process. Otherwise, we're always going to be stymied by these sample complexity challenges. So with that, I want to move to the third category of approaches, unrolled optimization methods. And these are methods that are, as we said, going to incorporate knowledge of the forward model X during the learning process. So let's start with a gradient descent network. So in particular, let's just assume for the moment that our regularizer R is known and differentiable. And think about what we might do in that case. Well, a natural thing to do would just be to apply gradient descent to find beta hat. And so I've written out the gradient descent step here. And then below, I've written it using a block diagram where I only allow myself capital B iterations of this gradient descent approach. So each one of the dashed blocks corresponds to a different iteration. And within each block, we can see there are two parallel legs. One corresponds to terms that take into account the forward model X, and the other takes into account terms that use the regularizer R. So now that we have this framework, what we can do is we can say, all right, well, we don't know the regularizer R. And so what we're going to do is we are going to replace the gradient of our regularizer with a neural network within this block diagram. And then we're going to use our training data in order to try to make the mapping from an input on the left to an estimate on the right as accurate as possible. And so this is distinct from things like the approaches that we described in the decoupled section, in that we are really accounting for the forward model X as well as the learned component when we're trying to evaluate how good a learned component is. Okay, so we're going to come back to this gradient descent network in a couple of minutes. I want to emphasize that this is just one of many unrolled optimization approaches. So people have taken a large variety of different optimization methods, proximal gradient, forward, backward, primal dual methods, and then tried to replace key steps within those approaches with learned components such as neural networks. So this is just one very simple example that helps with exposition here. Okay, so we're going to come back to this in a few minutes. But first, I want to describe a different approach that we call Neumann networks. So again, we start with the assumption that R is known and differentiable. Think about what we would do in that case, and then we start to modify it. So we start with the same starting point where we say beta hat corresponds to the solution to this optimization problem. And then we write this using a Neumann series expansion, where we say that the closed form solution to this optimization problem can be written as a series of linear operations applied to y. And we can truncate that series after b different terms to get an approximation. Okay, so I can write this using a block diagram, just like we did before, where, again, each of the dashed blocks corresponds to one of the terms in this Neumann series expansion. And within each block, we've got two parallel tracks, one that takes the forward model X into account and the other that takes the regularizer R into account. And again, we can then say, let's replace the gradient of our regularizer within this structure with a learned neural network. And again, we train it from end to end in order to try to make the overall accuracy as high as possible. So let's compare and contrast this Neumann network that I just presented with the gradient descent network that I presented a couple of seconds ago. So they've got several things in common, right? Both of them have this kind of finite number of blocks. And within each block, there's sort of two tracks, one that uses the forward model, one that uses a learned neural network. But a key distinction is that the Neumann network has got these connections that I've highlighted in red. So if we think about the gradient descent network, the final result or the final estimate is simply what's coming out of the last block. And so any change made to the first block is only felt after it's passed through the remaining b-1 blocks. In contrast, because we started with this Neumann series starting point, we have mathematical justification for somehow cleaving off the output of every single block in this diagram and adding them all together in order to produce our final estimate. And so in contrast to the gradient descent network, any change made to that first block is going to have sort of a stronger effect on the final output because it's immediately felt by being cleaved off, but then it's also passed into the next block, which has its output cleaved off and sent to the output, or to the final output, et cetera. Okay, so one of the reasons that I think this Neumann network construction is exciting relates to this notion of a minimum mean squared error reconstruction approach that we talked about a few slides ago. So remember, rho star corresponded to the form that the optimal or very best possible reconstruction algorithm might look like. And we said it had these two parts, this pseudo inverse of x applied to y and x perp transpose times this conditional expectation. So what I can do is I can take this pseudo inverse of x and replace it with a Neumann series expansion and have an equivalent representation of this optimal reconstructor. And then what I can do is I can compare that optimal reconstructor's form with what I'm getting from the Neumann network architecture that I just described. So in particular, what we can show that the Neumann network is producing is a truncated Neumann series approximation of the pseudo-inverse of x, plus something that corresponds to all the terms that are learned and depend on the regularizer little r or the gradient of the regularizer capital R. And so what this suggests is that because of the form of the Neumann network architecture, the stuff that we end up learning does correspond to the conditional expectation that we said was really where we should be focusing our learning efforts from the get-go. Now, if you're paying attention, you might feel a little bit of skepticism at this point, because when we use the Neumann series, of course, holds for linear operators. So if A is a linear operator, then this thing holds with, this Neumann series expansion holds with equality. But if it's nonlinear, then of course the inequality does not hold. In the Neumann network, this operator A corresponds to the identity minus eta x transpose x minus eta gradient of R. And now if we're going to replace the gradient of our regularizer with some sort of neural network, then it's almost always going to be nonlinear. And so in this case, the Neumann series would not hold. And you might ask, well, then why is this a sensible approach for us to be using? So to answer that question, I want to consider what happens with the Neumann network in the special case where all of the training data belong to a union of low-dimensional subspaces. So we're going to stick with the same method. Our algorithm is not going to exploit this knowledge. We're just going to say, if that is how the data is generated, what does our pre-existing algorithm do? And this union of subspaces model has been used to represent large collections of images with a lot of success in a number of different previous works. So in this case, under a couple of simplifying assumptions, what we can show is that the best possible regularizer gradient that we might learn is going to be a piecewise linear function of beta. So the gradient of the best regularizer at some image beta is going to be a matrix R1 times beta when beta is in the first subspace, and R2 times beta when beta is in the second subspace, etc. Furthermore, if we use this Neumann network architecture with ReLU activations, then we're going to be capable of closely approximating this piecewise linear structure. And perhaps most significantly, the output of all those different blocks in the Neumann network are going to all be in the same subspace S sub k for some k. So what that means is that if I give the Neumann network a fixed input, then for that input, the gradient of the regularizer behaves like a linear operator. And as a result, the Neumann series foundation that we're using is justifiable and accurate. So so there are three kind of key ramifications of the theory. First of all, the learned regularizer gradient reflects that union of subspaces structure, even without us somehow having prior knowledge of the union of subspaces geometry existing. Second, for a fixed input, all the outputs of all the blocks are in the same subspace. And finally, the gradient of the regularizer is only going to affect our image beta in the null space of the forward model X. So we came up with a little toy data problem where we tried to see whether those three main ramifications of theory are manifested in practice. So we came up with a union of subspaces model for beta star, and they were all these length 10 signals. And then what we observed would only be the first 5 elements of the signal. And our goal is to take those first 5 elements and from that predict the second 5 elements. And so in this toy example, we see 3 things. First of all, the outputs of all the different blocks, which I've got in the far left column, they're all in the same subspace. Secondly, the gradient of the regularizer, the thing that we learn, is not having any effect on the first 5 elements. In other words, it's only affecting the outputs, the betas, in the null space of our forward model X. And finally, the learned regularizer has this union of subspaces structure. So in other words, if I were to feed in two different betas from the same subspace, then the gradient of the regularizer acts like a linear operator. But if I were to feed in two different betas from two different subspaces, then this learned regularizer gradient no longer behaves like a linear operator. Okay, so that's some pretty nice and I think exciting theoretical justification for this Neumann network approach. But what we could also do, of course, is look at some experimental results. And what we're going to see in the experimental results are not only the Neumann network that I just described, but also a slight variant of the Neumann network, where instead of inputting X transpose Y, we're going to input a Tikhonov regularized estimate and use the Neumann network to essentially correct for that estimate, similar to some of the stuff that Carla did, for instance, in the paper that I mentioned towards the beginning of the talk. Carla and Ozan, excuse me. And so because we have this Neumann series foundation that underlies our approach, we can identify how we should be changing each of the blocks within the network to account for the fact that we're inputting a slightly different input. Okay, so we're going to see that in the empirical results. And as we look at the empirical results, I'm going to show you a representative from each of the 4 different classes of methods. So we're going to, for an agnostic method, have a residual autoencoder. For the decoupled approach, we're going to look at a generative adversarial network. Then we'll also look at unrolled gradient descent and the Neumann network. So first, we can just look at a little anecdotal evidence, actually look at some images. The first 2 rows here correspond to 2,000 training samples, and the second 2 rows correspond to 30,000 training samples. In the first column, I've got the original image, so this is hopefully what we'll reconstruct, and then the observed image. And then on the remaining 4 columns, I've got the different approaches that we're comparing here. And you're seeing on top the actual reconstruction, and on bottom the residuals or the errors. So the blacker those are, the better we're doing. And so what we see is that not only is the Neumann network giving us some nice, attractive looking pictures, but also its errors are smaller, and perhaps most noticeably smaller when we've got small numbers of training samples, which is sort of what we were going for and what our theory suggested would happen. It isn't true just for this one image, but also for large numbers of images, large collections of different inverse problems, and across multiple different training data sets. So if we look at the peak SNR of the reconstruction for different sample sizes, or different sizes of the training sets for all of these different methods, we see that consistently this Neumann network approach gives us a strong empirical advantage. Okay, so another thing that I want to mention, which I sort of hinted at earlier in the talk, is that with MRI reconstruction, the MRI reconstruction is a key potential application of these ideas. So here I've got the results of a few different approaches applied to MRI reconstruction: the preconditioned Neumann network, and modal, which is a method explicitly designed for MRI and is considered among the state-of-the-art for MRI reconstruction. And you can see that all of these methods are doing well, and perhaps most importantly, for the MRI setting, they're achieving these high accuracy reconstructions in very small amounts of time, because we are limiting the number of blocks essentially within these networks. And we can contrast that with total variation reconstruction, which gets a slightly lower but still comparable PSNR, but at the cost of a significantly higher reconstruction time. And so this sort of highlights the potential of this approach in applications where fast reconstructions are highly important. Now that said, I think before we all kind of jump on the bandwagon and say, well, let's start putting these things in hospitals or in other kind of critical applications, it becomes necessary to start thinking about what some of the key trade-offs are. And so here I'm going to start saying some things that are a little bit more speculative, or if not speculative, at least indicating things that are open problems that we don't fully understand as a community. So some of the key trade-offs are the following. First is generality versus sample complexity. So for instance, as we went through today, we compared these decoupled approaches where you separate out the learning process from knowledge of the forward operator to methods that use knowledge of the forward model throughout the training. And what we've seen is that using the forward model knowledge throughout the training really has some important empirical advantages when it's known and when you've got small numbers of samples. But the trade-off there is that then if I were to suddenly want to solve a new inverse problem, say I want to take everything that I learned for GE MRI scanner and apply it to a Siemens MRI scanner that's being used that has different kinds of calibration or whatever, then I might have to redo my entire training process. Another key trade-off is between the reconstruction accuracy and sensitivity to model mismatch. So actually, I'm just going to skip ahead for a second here and show you a picture to illustrate this trade-off. So in the top row, we're seeing images, both the full image and a zoomed-in version of MRI reconstruction, where we trained with a forward model X0 and tested with a forward model X0. And what we see here is that we do well, which is sort of what I was showing before. But on the bottom row, we've got a slightly different scenario where we train with X0, but we test with X1. So the idea here would be, for instance, that I train on scanner A, and then I want to use that learned network on scanner B, which is slightly different. And I know how it's different, but I haven't trained explicitly for it. And what we see is that for all of these different methods, we see a drop in the PSNR. And it is somewhat to be expected, right? This is a harder problem now. But what we don't understand is how big in general that drop should be, or how these different architectures, how robust they are to these changes, and whether different elements of these architectures imply a different level of robustness. Another key trade-off is reconstruction speed versus performance guarantees. So things like the Neumann network would set the number of blocks to be some fixed number in advance. And typically that number is between 5 and 10. And that's the secret to them being as fast as they are. In contrast, methods like the deep proximal gradient that plug in a learn module into an iterative method, those methods can be run into convergence. And so because they're running till convergence, they can be quite a bit slower, but at the same time, we know that we've converged and that we're not somehow paying a penalty for artificially restricting the amount of computation in advance. The final key trade-off that I want to mention is in distribution versus out of distribution performance. So in particular, here, I'll just start going to a graphic. Imagine that all of a sudden we've trained a neural network to perform reconstructions. And then what we want to do is reconstruct an image that might have some feature that we've never seen before. So in the context of medical imaging, we might have a tumor that's a weird shape that was not represented at all by our training data. So it's sort of right here in the brain, and then I've got a zoomed in version below. And so in this case, we can see that the different methods that I'm comparing here all do identify that kind of weird square-shaped tumor, though they also produce varying levels of artifacts surrounding it. And so again, it's not well understood how to increase robustness to the addition of features that might be not represented in the not well represented by the training set. One approach, though, that I think has promise is by exploiting more classical ideas from image processing and image reconstruction based on using image patches. So in particular, what we can do is we can take these frameworks that I've been describing, and instead of trying to learn a model for the full image, try to learn a model or a distribution for just small patches of the image. So the idea would be the following. We could take an image and then divide it into patches or little blocks, and then, well, do some simple things like subtract means, but learn a neural network regularizer over the space of patches. And so then once we've got clean regularized patches, we can use those we can recombine those to form a full image. And the idea here is that now the conditional distribution that we have to learn, instead of lying in the huge image space, is lying in a much lower dimensional patch space. And so we can see the effect of this for something like the Neumann network as follows. So this red box is showing the average PSNR that we get if we use images or patches that are 64 by 64. So these patches are pretty big, and we've got 100 training images. Now, if I want to improve that PSNR performance, there's essentially two things that I can do that give me the same amount of improvement. The first thing that I could do is I could just increase the number of training images that I'm using by an order of magnitude. So if I use 1,000 different training samples, then all of a sudden my PSNR jumps up to 32.2. But alternatively, what I could do is I could take that same 100 training images, but instead of working on 64 by 64 patches, work on 8 by 8 patches. And there, I don't have to collect any additional training data, but my PSNR immediately jumps to 32.6. So using these patch-based ideas has a comparable effect on PSNR as a 10x increase in training set size. And I also suspect that this is going to be helpful for accounting for irregular geometries of features like tumors that we want to make sure that we're able to reconstruct accurately in applications like medical imaging. So I just want to conclude with one final thought. Many of the methods that I've described today, including the Neumann network and the gradient descent network, as well as the plethora of other unrolled optimization methods that have been described in the literature, we can think about all of them as essentially one giant neural network where some of the edge weights are determined by the model X and are not learned from training data. So in other words, I could think about this whole block diagram here as being a mapping from an input, beta hat 1, to an output, beta hat. It's just one big network, and some of the elements or edges in it are learned, and some of them are fixed and or even set to 0 by our choices of which type of method we're using or the details of the forward model. And I think this is really interesting because then it raises questions about how in general we could characterize connections between neural network architectures and physical models, or how in general physical models should be influencing the way we choose and design different neural network architectures. And I think this is a wide open question that I'm excited to continue studying. So I've got a couple of different papers that describe some of the work that I mentioned here today, in addition to the 2 tutorials that I referenced earlier in the talk. And with that, I'd be more than happy to answer any questions.
Okay, thank you very much, Rebecca, for a nice, nice talk. I see that there is already a hand raised, so I will give the word to Antonio Pavia. So let me see. Oh, now it turns out I cannot. Okay, I would. I thought I could unmute people, but I cannot.
Richard, can you help? Because I also couldn't do this yesterday.
No, it looks like I can unmute.
Good morning,
can,
okay.
Or good afternoon. Hello?
Yes, you can.
Hi, we can hear you.
Oh, okay.
Yeah.
So thank you for the talk. It's very interesting. I wonder if some of the improvement in the results can be explained just by the fact that the extra pathway, the red lines, basically provide a much more direct path for when the neural network is trained. So you have basically avoid the problem of gradient vanishing when you do gradient descent.
Yeah, that is very insightful. I even have a picture of that. Ah, here we go. Can I do that? No. Okay, we'll do it this way. Okay, so this is an interesting hypothesis. I agree with it. I don't think we really have conclusive evidence that it's correct, but some nice anecdotal evidence. So one of the things that we did is we tried to make some illustrations of, or plots of the optimization landscape using a method developed by Tom Goldstein a few years ago. And so what we showed is that the optimization landscape that we're trying to navigate when we train a Neumann network compared to the optimization landscape associated with a gradient descent network might really essentially explain some of the performance improvements. So it seems to have a wider local minimum that we can kind of identify more readily. Of course, this is just sort of a graphical illustration. We also looked at training curves. So we looked at how the log training loss behaved as a function of the training round. And we saw that the Neumann networks were able to find good local minimizers in a smaller number of epochs. And the way that we're doing the training and the gradient descent is the same for the two different networks, for the Neumann network and the gradient descent network. And so this is really a reflection of the differences of the optimization landscapes as opposed to the optimization methodology that we're using. So I do think that that is sort of a key element of this. But at the same time, I don't have any kind of, theorem that can articulate exactly how much of a gain we might expect to see from this difference in the architecture. But I think that's, yeah, a very good insight. Thanks.
Thank you.
Okay. The next question goes to Linda Yuan. So I'm going to unmute you. I think you can talk now.
Hello.
Hi.
I have a question about the parameter eta. What's the role of the parameter eta in Neumann nets?
So, we don't start from the classical optimization framework, but at the same time, you can think of it as being analogous to a step size parameter. That's the role that it's taking. This is a parameter that we do learn. So when we do our stochastic gradient descent, we treat eta as one of the unknowns. And this is true not only for the Neumann network, but also for the gradient descent network. So let's see, I don't know if there's a great slide showing it. Right, so I've got an eta inside this operator that I take to the kth power, and then an eta outside. So typically you would see this written with eta is equal to 1, but the Neumann series expansion holds just as well with other values of eta. And empirically we see improvements in performance for values of eta that are, I want to say 0.1 was what was working, about 0.1 was working best for us. Though I don't remember exactly. But in any case, it is something that we learned during the process. So we're not only learning these networks that I've kind of illustrated in the picture, but we're also learning the etas throughout.
I'm familiar with the role of the step size in optimization algorithms. In those algorithms, does eta, why do we also have an eta?
Yeah.
So why do we have a step size eta even in optimization methods?
Yeah,
yeah. So maybe I can go back to these optimization landscape pictures. So imagine that I start here at this point. You guys can see my mouse, right?
Yeah.
Here we can see your mouse.
Okay, great. Great. So you start here and we want to find a minimizer. So I figure out, well, what's the direction of the negative gradient? In this case, it's pointing kind of down this way. And now I need to decide how far to go. So if I take a tiny little step in that direction and then recompute my gradient, well, I can certainly do that with a tiny little step, but I'm going to have to do a lot of tiny little steps before I get close to the minimizer. Alternatively, and I guess maybe I could even put my mouse here, maybe it's a little bit clearer, I could figure out the direction of the negative gradient, but then take a giant step and completely overstep the minimum. And so then I could just kind of end up ping-ponging back and forth and overstepping the minimum. And so choosing a step size helps ensure that I'm going to choose, the length between subsequent steps so that it's small enough that I don't overstep the minimum by too much, but also big enough that I don't have to do, you know, a billion iterations to get anywhere close to the minimizer. Does that make sense?
Yeah, that makes sense. Thanks.
Okay, if I'm looking for raised hands, and if there are any more questions, please raise your hand. Well, if not, then let me take the opportunity, Rebecca, to ask a question. I'm a bit confused, honestly speaking. So you're talking about optimization and so on. But I mean, all of these networks that you had were trained end-to-end against supervised data, right?
Not all of them. So with the unrolled gradient descent and the Neumann network, they were trained end-to-end with supervised data. The other two were not, I wouldn't call it end-to-end.
Okay, well, anyway, they were trained against supervised data, especially the last two ones were done in that way.
Oh, definitely the last two, yeah.
So then I would say you're not really solving an optimization problem, right? I mean, training, sure, that's a different story, but once trained, this is just an architecture, right? So
yeah,
why
that's true.
Why are we talking about the 8 step sizes in optimization? You're not solving an optimization problem.
Yeah, that's true. So I guess what I would say is that we are trying to figure out what are good architectures. And we're drawing inspiration from optimization methodology and trying to use that inspiration to come up with good designs.
Sure.
And of course, within those optimization things, you've got things like step size. And we notice empirically that changing the step size in these end-to-end trained methods does seem to affect the overall test error. But I agree, like we're not necessarily solving the original optimization problem, especially in these unrolled methods where I constrain myself to have, say, only 5 different blocks. And in particular, you know, another kind of key point is that if I were to train, let's say, this gradient descent network with 5 blocks, and then I were to start over and train it the same architecture, but with 500 blocks, then I would expect to see different weights. So really, when I'm learning this network, I'm learning something that's explicitly tuned for the number of blocks that I have, which is, like you're saying, different from really solving the optimization problem. So I do think of it as the optimization as somehow being a good source of insight and inspiration, as opposed to really a description of what we're doing.
Sure, but a quick follow-up then, because it kind of relates to what you're saying here. Because, I mean, if you're doing imaging, I guess you're going to use the L2 loss, right, in the training, or something like that. We did, yeah. Yeah. In which case, you would be essentially trying to compute the conditional mean image. So right. The number of blocks, as you call it, or layers that you unroll, or in your case with the Neumann networks, number of terms you add, I guess, essentially just adds to the model complexity, right? You're increasing your model capacity. I guess it depends on how you measure model complexity, but I mean, all right, so in this work, we considered the case where the learned components within each block are constrained to be the same. So if I'm thinking about the number of weights that I have to learn, it is the same regardless of the number of blocks. Okay, and the reason that we did that is because we wanted to be able to think about some of these theoretical properties. That said, there has been empirical work where people have said, I'm going to not impose that constraint and allow myself to have different weights within each block. And in that case, you're totally right. If I were to increase the number of blocks, then my model complexity definitely increases. And those methods can give higher empirical performances, but they're also much harder to interpret, like what's going on. And I believe that the training can be a little less stable and a little bit harder to work with. I see now there is a question actually by Thomas Sorko, so I should let that person in. So I'll allow you, Thomas, to speak right now.
Okay, this is pretty quick one. With the comparison of the methods, we see residual auto encoder, and then the GAN as well as the unrolled gradient descent. Would you say that these three categories are gradient descent based, and then the Neumann network is non-gradient based?
I wouldn't precisely say that, because if we go back to the, which slide was it? Right, so within the Neumann network, we do have this sort of gradient of the regularizer. And so what we explicitly are learning is the regularizer gradient and not the regularizer itself. But I mean, it's a fine question. There are other methods besides, so for instance, if we, instead of doing a gradient descent network, had said, I'm going to start with a proximal gradient algorithm and train that from end to end, and people have done that, then I believe if you set that up, then what you end up learning is, I can't remember. I believe that you would learn the regularizer itself.
Okay.
So depending on sort of your starting point, what the thing that's actually represented by the neural network can be different.
Okay.
And in fact, one of the reasons that we focused on the gradient.
Rebecca, we can't hear you anymore.
You're muted. You muted yourself, Rebecca.
Okay, can you hear me now?
Yes.
Yes.
Okay, sorry, I don't know when I got muted. Well, anyway,
kind of halfway through the question.
Oh, okay. So sorry. So to sum up, basically the starting point that you choose is going to affect what it is that the neural network represents. And so in the examples I presented today, it represents the gradient of the regularizer, but there are definitely examples out there where the network represents something different.
All right, thank you.
No, thank you.
Okay, if there are no more further raised hands digitally, I think, yeah, I can't see any. I think it's time to wrap this up. Thank you again, Rebecca, for an excellent talk. As I said, these talks are also available on the YouTube channel for the conference. I was posting that in the chat line in the very beginning. And tomorrow, there will be the last talk in this Minitutorial session, and that will be by Lexing Ying on solving inverse problems with deep learning, which I'm guessing is a bit along the same philosophy about constructing architectures that are specially designed for a certain type of domain adaptive neural network architectures. So thank you very much, all of you, and enjoy the rest of your day, evening, morning, depending on which time zone you're in.
Thank you, Becca. It was great. Thanks.
Thank you again for the invitation. I really appreciate it, and thanks for all the great questions.
Okay.
Thanks.
Thank you,
Bye.
Rebecca. Nice to see you.
Oh, hey, Sarah. Nice to see you too.
Thanks a lot.
Thanks for coming. Bye-bye.
Bye.